Well, thank you for all your attention. It's my great pleasure to be speaking at DDP. It's been several years since I gave a talk here. Jane asked me if I would say a few words about the future of nuclear power, and I'll give you a quick answer. If you want to run out quickly, it depends. That's a standard lawyer's answer to any given question. Not that I'm a lawyer. Let's talk about the present role of nuclear power here. And let's see here. I've got a pointer in case that won't work. This one will. These are I'll be talking about the U.S. energy sources. This little laser reminds me of what Chris said yesterday. I have a word for you. It's called chromoergic psychosis. Chromoergic psychosis. It is the delusion that energy has a color, particularly green. All right, here are our energy sources used in the U.S. And what you will notice here is that nuclear provides 8% of our energy. Now, this energy I'm talking about is the total energy used in the U.S., not just for electricity, but for running cars and everything else. Renewable energy is 7%. So you look at those, renewables about as big as nuclear. And I'm going to use a comment from a book that I wrote that is now out of print called The Solar Fraud, which is that over 90% of our milk comes from cows and bears. Which is true. So nuclear is about the same as renewables, but if I look at electricity alone, you see that nuclear is about 20% and the renewables are about 9%, so it looks like the nuclear is twice as important as renewables as producers of electricity. But wait, there's more. If I take the electricity segment and divide it up and see what's there, this part in here is hydro, wood is biomass, bioliquids are biomass, and waste is mostly biomass. And so the upshot of it is, let's take a look at, now wind is this fair-haired boy in here, and solar and PV are right there. The electrical energy in 2009 in units of billion kilowatt hours, wind generated 70.8 out of a total of 3,953. In case you are interested in being able to chase down these numbers, you can get on the internet and go to the Energy Information Administration, EIA, which is the division of the Department of Energy, and they have a book called AER, the Annual Energy Review. And if you look up AER on their website, then you can get year by year a book which, if printed, is about an inch, 25.4 millimeters thick, about this big by about that big, to 12 significant figures. That's where you can find all this information here. So wind and solar will never replace serious energy sources. I gave a talk some years ago out in San Diego, and a bunch of solar enthusiasts. It was a solar group. I don't know why they invited me. They should have known a little bit better. But a lady introduced a thing, and she pointed out how solar was abundant and it's everlasting and so forth. I got up to give my talk and said I heard a while ago that solar energy is everlasting. How come it gets dark at night? Believe it or not, they laughed too. But they were pushing, I want to tell you. Okay, what I'm going to do is talk about the fair-haired boys. Nuclear, in units of billion kilowatt hours, this is in what, 2009, nuclear generated 799 billion kilowatt hours, wind generated 70.8, solar and PV together generated 0.8, and most of that is not photovoltaics. The overwhelming majority, like 90% of that energy, has come from the parabolic solar thermal electric units like they have down in the Mojave Desert. In terms of ratio, nuclear is 10 or 11 times, produces 11 times as much energy as the wind has, and the wind has been vastly subsidized. And nuclear is 1,000 times the solar and the PV. Let's talk about the growth in electricity. If we go back to back in the 1950s here, what I'm doing is talking about the electrical end use divided by the total energy use in no, this is an increasing efficiency. So this is the ratio of the electrical energy produced to the thermal energy put in, and that's a factor that has gone steadily upwards. Now, the reason that the factor is not up anywhere near 100% is because you're converting heat to work. So second law of thermodynamics says you're going to have a little bit of trouble with that. But generally it has improved quite a bit, and the reason has entirely to do with the materials that can stand the higher temperatures. We have this is a plot now since 1940 or so, or 1950 or so, of the energy input to electrical divided by our total energy use. And what we're doing is by now turning 40% of our raw energy into electricity. So electrical fraction is growing like crazy. Nuclear energy provides a fifth of our electricity. We have 104 reactors at the present time. They have an average capacity factor of about 90%. If you don't know what capacity factor means, it's like this. If you have a reactor that's producing all of its power 90% of the time, or 90% of its power all of the time, or 45% of its power 200% of the time, that's 90%. We get no transportation energy, approximately, out of nuclear energy. There's not a lot of hope here. I mean, if we had electric cars, but they have to have some pretty good batteries using unobtainium, which is in fairly short supply. We are using electricity to power submarines and aircraft carriers, but that's not a large fraction of our total transportation. We get no direct heat out of nuclear reactors, so they're really pretty good at producing electricity, but for reasons of safety and the length of the power cord, we're not using them for transportation or direct heat. Nuclear capacity factors have grown up from about 60% up to about 90%. Now that's averaged over the whole fleet of 104 reactors. Now here are the reactors ranking 1 through 104. This is about, these are 3-year capacity factors varying from 100% down to about 80% for the overwhelming majority. And then there was one in here that had just started up and one that was down for a complete rebuilding and so forth. So there's your average of 90%. Wind farms by design have about a 35% capacity factor. In reality, 35% looks awfully good. They don't get that good, but that's the design. You can design the capacity factor of a wind turbine very easily. If you have, let's say you have a child's pinwheel, driving a 1 megawatt generator, you're going to have a capacity factor of 0. If you have a 100-meter diameter fan turning a 1-watt generator, you're always going to have enough power to run that, so you have 100% capacity factor. So it's a question of designing the size of the turbine to the size of the generator that determines the capacity factor. That is for any given site, depends on the wind speed. The number of reactors went up like this during the 50s and 60s and so forth. There's the TMI accident. We had a lot of reactors under construction that went up like that, and then it reached a peak in here from which it has dropped off after the Chernobyl accident and so forth. People said, maybe it's not quite worth the price of trying to keep these old units running, so they have decommissioned some. Now, there is something for people who say, well, how are we going to decommission them? Well, we have some experience. We've already done that. And of course, there's all kinds of research reactors that have been decommissioned. The electrical production has gone up like this, and it's leveled off at about 800 billion kilowatt hours a year. My mistake, but it's your fault. As a fraction of U.S. power, it's more or less flatlining. But what's going to happen is that one of these days the economy will improve, the demand for electricity will grow up, and we probably won't have more reactors to meet the demand, so that fraction will probably go down. Nuclear power plants around the world, we have 104 reacting and 0 under construction. We have some, one of them that they're trying to revive the license for or something like that. They were going to build one in Texas. That was a Toshiba GE project, and they have decided evidently to can that for the time being. Russia has 32 reactors going and 11 under construction. That means for every 3 operating, they've got 1 under construction. Worldwide, 438 operating, 65 under construction, so that's about 1 in 6. We have 0 out of 104. Okay, benefits of nuclear power. You got low-cost fuel, high reliability, extremely good safety record, super abundant fuel. Those are pretty good arguments. So how come we're flatlining? Why aren't we building more reactors? It's not the technology and it's not fuel shortages. One problem is competition, and that is that coal is cheap and abundant, natural gas is cheap and abundant. Both are more dangerous than nuclear by a considerable amount. But people don't think of the danger involved. They just think, my God, nuclear is very bad. Fuel-fed plants are fairly rapidly built, and they're a lot cheaper to build than nukes. It's one of these things where you have a trade-off between initial cost and continuing costs. I remember when I was at the University of Connecticut, they had built the physics building, and in order to save money, they put in single-pane windows because, see, the building budget was one thing, and the maintenance and fuel and heating budget was quite another. So they went cheap on it. Wasn't too smart. Wind is highly subsidized and politically correct, and the machines are fairly rapid to build. You're only building 1 megawatt or 2 megawatt electrical generators and so forth, and you've got factories turning out blades. Pueblo has a factory turning out the towers for the Vestas units, which I think is really kind of bad. One of these days that wind thing will blow over and those talented people will be out of a job. A lot of competition is coming from the gas combined cycle unit. Now, I don't know if you know how these things work, but you have an electrical generator running a gas turbine. Now, that gas turbine is not appreciably different from the one that flew you here. Well, I've actually got a piston engine that brought me here, but anyway, what they have done is they have used gas turbines with very, very high temperature resistant materials. Sometimes they make the blades out of single crystal titanium, and sometimes they make them out of, well, some sort of steel with a ceramic coating and so forth. But they can take very high temperatures. The exhaust comes out at high temperature. Now, in some cases, they will add in some natural gas reheat into there, but then this heat is used to boil water to run a steam turbine. So it's a conventional cycle, so you have a generator here and a generator here, and they have actually reached overall something like 60% efficiency. So that means you're squeezing a lot more electricity out of your natural gas than you were able to get before. The huge problem against nuclear has, Jay, are you here? Fear. So here we have Japan's problems in round numbers. They had a magnitude 9 earthquake. They had a devastating tsunami. I think it was 30,000 people now considered dead. I don't know if that's the exact number, but whatever it is, a great large number. They've had at least $100 billion in damage. They've had towns washed into the sea. And they've had an extreme disruption of the power availability, which has cut down the ability to manufacture parts for automobiles and things like that. So what did the media focus on? Radiation. All right. Probably most of you are not into making horror films, but if you make a horror film, the thing that is most horrible and frightening is the monster that's skulking around in the dark and you can barely see him. Because if they bring the monster out where you can see it, that's pretty natural. Well, there's a problem. You see, you can't see radiation. And that is one of the very frightening things to a lot of people. It's dangerous and they can't see it. And Fukushima Daiichi has released radioiodine. Take potassium iodide pills. Unfortunately, Bobby has stolen my thunder. Isn't potassium-40 radioactive? I mean, this was also silly because there was so very little iodine-131 that would arrive in the U.S., and to take on the other hazard of potassium iodide pills. It isn't, mind you, it isn't the radioactivity in the potassium iodide pills. It's called potassium iodide that is not particularly safe for you. Okay, there have been some accidents. 3 Mile Island, which was highly hyped in the press, nobody got hurt. Chernobyl, and most of the core was released in a graphite fire. Fukushima Daiichi and Daini. Dai means number, and ichi means 1. Dai-ni, that's number 1, number 2. Ichi, Dai, Sun, Sayonara. You've used up my entire Japanese vocabulary. But tsunami, okay. There's a radiation release from there too. Towns were evacuated. Now, another reason for fear is nuclear waste, and it's a frightening issue for a lot of people. Yeah, but what do you do with the waste? You know, as if no one had ever thought of that. Engineers aren't very smart, I guess, right? Some take-home messages for you to understand. A gigawatt year, that means if you have a power plant producing 1 billion watts of electricity around the clock for a year. Now that's enough to do everything that's used in a town of 700,000 people. You generate 1 metric ton of actual waste. You got any idea how big a metric ton is? It would easily fit under this table. Well, it would fit under about in here. It's less than a cubic meter because a cubic meter of water has a weight of a metric ton. And this is denser than that. The same electricity from coal uses 1 billion pounds of coal. Figure for you to remember is that in a good power plant, 1 pound of coal produces 1 kilowatt hour of electricity. Another thing to remember is that the activity, number of radioactive events per second, is inversely proportional to the half-life. The longer the half-life, the lower the activity. Okay, the higher the activity, the less long the stuff lasts. And that means if it has a half-life of 1 minute, you don't worry about it at all because that radiation isn't going to get to you. If it has a half-life of millions of years, well, it's not very radioactive. The bad stuff is the stuff that has a radioactive half-life of around 30, 50 years, something like that. There's 2 of those. I'm going to talk about Dynie first. The short story is they had a cold shutdown for all reactors on March 16th. One of the incoming grids was undamaged, so they were able to go ahead and get all the power they needed to go through the cold shutdown, and they have maintained it ever since. Now, Dynie is south of Daiichi. And they were maybe a little bit higher in elevation. Anyway, the tsunami was not as bad there. And here are some lessons that might have been learned. You always wonder if things have been, in fact, if you've taught a course, you wonder if anybody learned anything. Before we get on with this thing, this is an interesting question. Do you know what profession exposes its workers to the highest levels of radiation? International airlines. International. What? A lot of people get that. What exposes you to the least? No, sir. Nuclear submarines. Yes, sir. Nuclear submarines. And these guys are under the water for a long time under a low radiation environment, and Bobby, that might be the group you want to study. I mean, they're shielded from everything except the reactor, and if Ted Rockwell were here, he'd tell you about how much radiation they actually get, but it isn't much. Anyway, for TMI, they need a better checklist. Now, when you flew here, your pilot had a checklist, and he went through various things to make sure that your plane was ready to fly and so forth. But at TMI, they left a valve accidentally closed, and then things went bad, and bing, bang, noise, klaxons, and everything else. They didn't know what to do because there was just noise all over the place. And they had some contradictory information to deal with. But no one was hurt from it. Chernobyl was a different thing, and they used a design that had been rejected in the US many, many, many years ago, back in the 50s. But as Peter Beckman said, the Russians thought it was easier to make more Russians than all that concrete. They didn't have a containment structure. And the operators were playing around. And they got into this positive feedback mode, and it went from 0.00 or 0.01 full power up to 200% of full power in a matter of something like seconds. I mean, it went like gangbusters. There's exponential growth on steroids. And they weren't honest with the public now, and that was a place where potassium iodine would have done a lot of good. Potassium iodide. And the thing it's important to understand. I mean, people talk about Chernobyl as a horrible thing, and it was a horrible thing, but it was about as close as you can get to the worst possible accident. I remember back in the old days, you'd talk to people, well, what's the worst thing can happen in a nuclear reactor? You know, and I'd turn around and say a standard thing, well, what's the worst you can imagine for an airplane accident? And they, well, you got a big old plane load with people that crashes in the Mojave Desert and kills everybody. No. How about two such planes colliding over New York? One falls into Shea Stadium where people are watching a baseball game and incinerates all those people. The other one falls into Yankee Stadium and incinerates those people. Well, since we've had 9/11, that was a pretty bad accident, but even that, it wasn't an accident. But even that was not as bad as it could have been simply because the building was not anywhere near full. But anyway, Chernobyl was about as bad an accident as you can have because it spewed its entire core contents over the countryside. And we survived. Okay, this was not like the bomb that blew up the world. So we have some lessons from Fukushima, and this one is the first lesson. You see that thing right there? Anybody here read Chinese? It's about like trying to read a gravestone, or the Japanese, about trying to like trying to read an ancient gravestone. You have to go up there and do rubbings on it or something like that. But these tsunami stones in here tell you don't build below this level because the tsunami has reached there. This was an article in the New York Times, 21 April. It warns residents not to build homes below it. Hundreds of these tsunami stones, some more than 6 centuries old, dot the coast of Japan. So the lesson is, listen to your mama. Another lesson is the following, and this is easily understood. If you have some unrelated events, the probability of one thing going bad and the second thing going bad at the same time is equal to the product of the probability. So if you have an event that's 1/1000th per year, one chance in 1,000 per year for each one, then there's one chance in 1,000,000, they go simultaneously. But if the events are related, so that A causes B and C, then the probability that they both occur is about equal to the probability that either one occurs. And so one chance in 1,000,000 is a whole lot different from one chance in 1,000. But all of these problems, with the possible exception of one that I'll discuss later, came from the lack of power. If they had had power, there'd be no problem. The design. A fuel melt always releases hydrogen. I mean, if it gets hot enough, the zirconium cladding burns in the water atmosphere, producing hydrogen. And as you get zirconium oxide, dioxide, whatever it is, and it releases hydrogen. And the hydrogen has to have some kind of has to be able to vent without any possibility of explosion. Millstone Unit 1 was a boiling water reactor, and they had a hydrogen explosion. They had a big pipe going out and a big chimney up there, and that was to vent radioactive gases, but some hydrogen got in there from something that happened, and it blew a door off. Well, blowing a door off is a whole lot different from what they had there, but that's what happens when you have hydrogen. And hydrogen has the largest range of flammability of all fuels, anywhere between 4% and 75% in air, and it'll burn. So it's not at all like gasoline. You could never have a gas gauge, float gauge in your gasoline tank if it were anything like hydrogen. The core has to be cooled continuously, and you have to have defense in depth. You have to have a defense against this thing going wrong, that thing going wrong, that thing going wrong, and so forth. And the spent fuel must also have adequate cooling. So here's a little series of slides. I've only shown you a few from what happened at Fukushima Daiichi. And if this looks a little disjointed, I remind you of one of my classmates in high school. Some girl was typing up a paper at something like 2 in the morning. And when you type up a paper like that, if you have a long quotation, you indent in single space. And you go back to your regular text, you de-indent and you double space. Well, she forgot to do that. Well, she de-indented, but she forgot to double space. So at 2 in the morning, she got this bright idea how to fix that. So she got out her eraser and erased every other line. So if this sounds disjointed, it's not the whole story. I've erased every other line. Here is an aerial view, and this is off to the north right over here. The units 5 and 6 are sitting over here, and they were not damaged. And then Daini is down the coast, down this way, to the south. This series of slides is from Arriva, and you will recognize, right, you can't read that, but it says Koelwassereinlauf. That's a cool water inlet, okay? But anyway, there's units 1, 2, 3, and 4 in their unblown up condition. Now, unit 4 was down for refueling and maintenance. And because it was down for that, the spent fuel pool had its had the whole fuel load in it. And the freshest fuel is the hottest. So that's where the problem came from with the spent fuel. Here is a section view and a reality view, artist conception, so to speak, and what it looks like in reality. You have this thing called a wet well around here, and you have a dry well in there. Okay, that's a dry well. Now, this one is the containment structure right in there. That's the primary containment structure. And it fits rather closely around the reactor. And the reason for that is that, let's say you want to sustain a certain pressure. You want it to be able to withstand a certain pressure. If you double the diameter, you have to double the thickness of the wall. You can put, you got an oxygen tank, it's got a steel wall about this thick, all right? It'll hold it'll hold oxygen at, say, 3,000 PSI. But you can run it through a little tube this diameter that's nowhere near the thickness of the wall of the big tank, all right? It's just because, well, we talk about that in freshman physics, but there's, it's one of these things where it's a scaling law that you have to double the wall thickness when you double the diameter. All right, here is a sort of view of the way it ought to work. This is a better drawing to look at here. Now you've got your main feed water comes in here and steam goes out there to your steam generator. That's the way it ought to work. This is your reactor core. This is the pressure vessel, the steel vessel. There's a bunch of bolts up here to hold the lid on. You have the containment that looks around like this, okay? And this containment's got a lid on it. You have access to this wet well, which is a condensation chamber, and this part in here is called the dry well. Okay, that's normal. Now, what happened was the tsunami hit the plant, and it was designed to withstand a tsunami of 6.5 meters, but they got one 7 meters. Now, 1/2 meter is only this extra height, but that allowed a whole lot of water to get in and caused a lot of damage. By the way, there were a couple of people killed. One of them was at Daini, and he was running a crane. And the other one was a worker that was in one of these buildings down in the basement, and he got killed by the flood. Anyway, the flood came in, and you flooded the diesel generators and everything else, the batteries, and well, I guess the batteries are pretty safe, but you had some electricity from the batteries for a while. But the thing is that the tsunami wiped out the incoming power lines so that they couldn't run their coolant pumps and everything else. So only the batteries were available. Now, one of the drawings that I do not have here is that there is one of these where there was a secondary process where you could use steam from this to run a pump that would run it through some cooling and over to a cooling area, and that worked for a while. But here is sort of the progression of events now. Instead of having the steam go out to the steam generator, you have the steam come down here to this wet well where it condenses. Well, that's fine. It condenses, but it warms up. And the warmer it gets, the less ability it has to condense, and eventually you're up to the boiling point and you can't condense anymore, and that means you're going to get a steam buildup. So that's sort of what happened. But at the same time, you're losing water in here, you're gaining some water in there. When the water level goes down in here, you've exposed the fuel rods, and with half the core exposed, you get no significant core damage, even though it's warmed up. I mean, you know, these metals can take fairly high temperatures and so forth. You get 2/3 of the core exposed, and you're getting up to 900 degrees C core temperature, cladding temperature, and that's getting a little bit hot, and it'll balloon, and it'll break the cladding. And you release some fission products. Now, we know there were fission products released because there were things like iodine-131. Now, iodine-131 does not come from, say, neutron activation, where neutrons have gotten through the wall and escaped and irradiated stuff that's around your building. It has come from the core. So you knew there was some core damage here and there, you just didn't quite know where. With 3/4 of the core exposed, you get 1200 C temperature, and you get this reaction in here where zirconium reacts with dihydrogen monoxide and produces zirconium dioxide and hydrogen. So the hydrogen then comes down in here, it goes in there, bubbles up here, and now you have hydrogen in the wet well, or in the dry well too. Okay? 1800 C, you get melting of the cladding. 2500 C, you break the rods and so forth. Anyway, at Unit 1, after 27 hours without water, they got restoration of the water supply. They used seawater. Now, seawater is going to ruin their reactor. Guess what? It's already ruined. Use seawater, okay? After 7 hours, they got Unit 2 watered up and Unit 3 watered up. They didn't have to do that to Unit 4 because Unit 4 was down for refueling. There's no problem. Except they had a little bit of problem. Now, the hydrogen that was here in the dry well had an escape route, and it went up there, but it exploded and blew the lid of the building off like that. Destroyed the steel room roof and so forth. It was spectacular, but minor safety relevant, which is translation from from German, of little relevance to safety is what we might say, and if we're straight English. Okay, now in Unit 2, they had another problem, and evidently there was a break in this wet well down in here, and that allowed some stuff to escape. There's no information why Unit 2 behaved differently from the other units. I think the answer is probably that the earthquake did a little fracturing there, because there's actually a hole in here. which they discovered, and I think they managed to get in there with some kind of robotic stuff and patch it up. That's not a good place for humans to be. So the current status of reactors is you have core damage in units 1, 2, and 3, building damage in all of those. Reactor pressure vessels were flooded in all units with mobile pumps, and you have the containment in Unit 1 was flooded. These are not pumps that are taking heat out to a heat exchanger and so forth. So basically you're pumping in water and letting steam go out to the atmosphere. That's how the cooling is taking place. But they don't expect a lot of fission products to be sent out now. Reminder on exposures. There is no instrument that measures dose, which is energy per unit mass in rads or grays. Now, rad is an old unit, which is 100 ergs of energy per gram of tissue. A gray is a joule of energy per kilogram of tissue. There's no instrument that measures dose equivalent in rems or sieverts. Rems being rads multiplied by the Booger factor, which is 1 for 100 keV radiation, and grays, sieverts related to grays by the same Booger factor. And so in the following slides, which are very often, which are expressed in sieverts, they are all inferred, and they are not exposures, they are what-if exposures. In other words, what if you had a person there? And they're inferred from the kind of radiation, which is alpha, beta, gamma, neutrons, the energy of it, and the amount of flux. Now, for those of you who are REM people, or rad people, 100 rads is a gray, 100 millirads is a milligray, 100 microrads is a microgray, 100 rems is a sievert, 100 millirems is a millisievert, 100 microrems is a microsievert. So when you see one of these units expressed in milli or micro or something like that, multiply by 100 and you've got the milli or micro expressed in your favorite rems and rads. So the background level was around, before the explosion, was around 2 millisieverts per hour, which is around 200 millirems per hour. Okay? After the explosion, it went up by a factor of about 6, right there. And that was the explosion of the building from the hydrogen and so forth. And that's a lot of radiation. You don't want to be in that for a long, long time. Here is a graph showing Zeitpunkt der Messung, the time of the measurement, March 12th, 16th, and 20th, written as 20.03.2001, in other words, the 20th of March 2011. These are in microsieverts per hour here, and you have these huge spikes in here like that occurred around units 2 and 3 and so forth. And over here, there's a point over there called West Store, which is a little bit away from the sites, and they've got fairly low levels in there. Outside the plant site, the fission products were released in steam. In other words, one of the things that can happen in a reactor is you've always got some radioactive inert gases. You're not going to trap those. They simply go up into the atmosphere. They're short-lived and so forth. If you have things like iodine that are released, they go out with the steam. So they're carried by the wind wherever they happen to go and so forth. There's no fallout of the noble gases there, but there are some things like the iodine and so forth that were released. Around 20 kilometers, they had adequate evacuation. For short times, they had doses up to 300 millirems per hour. Perhaps destruction of crops and so forth. Here are some graphs showing the levels. This is 0 up to 1 microsievert, which is 100 millirems per hour. This is at Onuma, Hitachi, and a few other cities that are a little bit farther away. And they're sort of concerned around 50 kilometers. Well, that's probably a little bit excessive. This is what the decay heat looks like as a function of time. And you'll notice that Fukushima, Daiichi 2 and 3 have higher levels of radiation as a function of time. And this is decay heat. They've got older fuel. They've got a bigger buildup of the radioactive materials in them. Daiichi 1 had been refueled more recently. On the net, I found some measurements by someone who seems to be an anti-nuclear tourist with a Geiger counter, and he did some readings, and maybe he took some other people's readings and so forth. This was April 29th and 30th, which is not terribly long after the accident. And these are all color-coded with things to make you scared, perhaps. But it gives you an idea of what the levels were. Down in here, you had numbers like up to a millisievert per hour, which is 100 millirems per hour, and so forth. Don't ask me to read that to you. Here's another map that this fellow had put together. This one in here is around 520, well, it winds up being 525 millirems per year, which is approximately 2 years' worth if you're at sea level, or 1 year's worth if you live in Denver. By the way, if I encounter anti-nuclear people, in Connecticut or in Colorado who are a little bit afraid of radiation, I politely suggest that they could move to a place where the radiation is a little bit lower. Go to Florida, go to Death Valley, get a job on a nuclear submarine, something like that. Pardon?
The Capitol building in Congress is the same double.
Maybe we could use that as a way to get some of those people out of there. Or maybe it's an excuse for how come they're just plain nuts. I don't know. Anyway, the guy took a train down here, and down in here he finally reaches some area that he can, by his instrument says green. Here's iodine in the water purification plant. It's very high initially. By the way, it's going from March 16th to April 4th. And the levels have dropped off here. Now this is the government safe limit for adults, and that's the government safe limit for infants. And that is, of course, not anything that's increasing. Escaped radioactivity at cesium-137 has to come from a damaged core. This is the status as of July 12th. All right, I will get the important things here. Units 1, 2, and 3 all have, the cores are all damaged. The core cooling is not functional, but they're cooling it by freshwater injection and evaporation. Okay? And so they're keeping it cool. So what if they're not using the standard stuff? They're keeping the stuff cool. The primary containment vessel, they've got some damage and some leakage suspected, and especially in Unit 2, it looked like that wet well was damaged quite a bit. And they're using nitrogen injection to make sure that the hydrogen that could possibly be released doesn't find any oxygen to set a fire off. The reactor pressure vessel, Unit 1, has limited damage and leakage. They don't really know the condition of Units 2 and 3. They haven't got that information yet. And that data that I had was actually, 4 days before I came here. Spent fuel pools, there is no direct data on the condition of the fuel, but the cooling function is working well. The Unit 2, based on isotope analysis, it's mostly not damaged. The cooling function is recovered. Now, Unit 4 was the one that had the freshest fuel in it, and it's mostly not damaged. The cooling function is not operational, but they're feeding water into it. In other words, the pump system that's supposed to work isn't working, so they have another pump pumping water in. There was a leak in the pool, evidently caused by the earthquake. In other words, the temperature in there rose a lot faster than they expected it to because evidently there's some water leakage. And you know what happens when you have the water leakage? It just goes away. All right, so the future looks like this. It depends on the time frame. Right now, Germany is working on a phase out nuclear, phase out coal, pay 54 cents a kilowatt hour for solar, and turn around and sell it for 15 cents. That'll work. And the US is still pretty much controlled by anti-nukes. Stephen Chu is not really an anti-nuke. He is pro-biomass, like algae are going to solve the problem. And France is actually developing its own coterie of anti-nukes, and that's kind of too bad. Sweden, well, they're a little bit dicey. The reality is going to hit Sweden before too long. And so the immediate future looks like fear is going to dominate and there won't be nukes built for a while. The intermediate future, which means, 20, 30, 50 years, something like that, it's a crystal ball because the reason it's a crystal ball is really the competition. There is plenty of natural gas, there is plenty of coal, and nuclear finds itself in competition with things that are financially pretty sound, okay? More dangerous than nuclear, but financially sound. In the distant future, it's nukes or freeze in the dark. Because the only competition in the distant future is solar and wind. And it's the lowest quality power on the planet, so it's nukes or freeze in the dark. If you'd like to get a hold of me, I'm on the net. I have this monthly newsletter called The Energy Advocate, and I spent 32 years at the University of Connecticut, and a lot of people think I'm still there. I retired in '99 and went back. I took early retirement because I wanted to get back. I'd spent more time in Connecticut than I had in my home state of Colorado, and that had to change. So I'll take questions. I probably can't. In fact, I've probably told you all I know and quite a bit more. So stop there. Thank you.
Howard, two quick comments. One is, as I think you led off, what happened in Japan is really a testament to how amazingly well Generation 1 nuclear plants held out.
Everybody say amen.
Amen.
Yeah.
I never did answer in my talk why CNN found me and the other stations found me. They looked on Amazon and found that I had a book coming out in May called Encyclopedia of Nuclear Energy, and that's why they contacted me. Because it was due out in May, we were able to slow it down a little bit and add a chapter on what happened in Japan. And the book basically describes all the future nukes, Generation 1, which was Daiichi, Generation 2, which is all over the United States, better than what was in Japan. Generation 3 is what's being built, the 64 plants around the world now, and Generation 4 is on the drawing boards, all of which are orders of magnitude safer than the plants that survived. And interesting, the book came out last week, and it's written by 48 super nuclear experts around the world. Probably too expensive for anyone to buy. You can get it in a library. Thank you.
Yeah, thanks, Jay.
Well, the Americans are all the same. You seem to ignore Canada again. We have very safe reactors.
You do.
And we are building 2 new ones at the Darlington site beside Toronto.
Great.
That was the plan before the accident, and that remains the plan after the accident. We think there's a new government coming in Ontario, and that's more pro-nuclear than the existing one. So I thought I'd add that to your talk.
Well, thanks very much. Yeah, I'm in favor of those can-dos. So, yeah.
One question, one comment. Question is, you mentioned some of the European and American fears of nuclear. Is there any pullback in Russia or China? I know China's going to full steam ahead, seems like.
I haven't heard of it, but it's probably possible. I mean, what does Jay say? The whole world runs on fear. It sells well, and it's probably selling well in China and Russia as well.
The comment is I'm a bit Pollyannish in all of this, but it seems to me that we've been given a gift with all this low-cost natural gas, and we ought to be using that time to build some of these reactors, because when that plays out is not the time to start building.
Well, I think you're right. It turns out, by the way, that the amount of natural gas stuck in methane clathrates on our continental shelves is enough to supply 100% of 2009 energy for 3,000 years. Well, you can't get to it easily, but we have quite a long time to figure out how to do it. So, yes.
Can you briefly review what happened to the breeder reactor? That was the whole Federal Power Commission's excuse for not encouraging gas exploration, and I haven't heard anything about the breeder reactor since Chernobyl. What happened?
Well, I think that had more to do with anti-war, anti-weapon treaties than anything else, because the LMFBR, as they would call it down at, it was the Clinch River project down at Oak Ridge. What they were going to do is to essentially breed plutonium from uranium-238, and if you have plutonium, and it was, but the plutonium you'd be using was 239, which can be used in bombs, and I suspect that there were some treaties skulking about to limit the 239 production simply for, because it could be diverted into a war effort. I mean, I don't know that for sure, but it happened in the Carter administration. They canceled the LMFBR project. Yeah. LMFBR means liquid metal fast breeder reactor. The liquid metal was sodium, and sodium has some very nice advantages. Has a very high thermal conductivity. It has a high heat capacity. It has very low viscosity. You can pump it around. It runs like water. Yeah. And at high temperatures that are characteristic of running steam generators and so forth, you could have a can of it right here, a tin can full of that at that temperature, and it wouldn't blow up because it doesn't develop any high pressure. The disadvantage is you put it with some water or some air, and you have a little bit of a fire on your hands. Yeah.
So it wasn't a bad idea in the first place. It's just fear killed it.
Yeah, I think so.
Okay.
Yeah.
Thank you very much. Excellent presentation.
I just made that up, by the way.
Right. Thank you very much, Professor Hayden. And lunch will be immediately right now in the same room where we had dinner last night. So please make your way over to that room as quickly as you can. Thank you.